Hi everyone. Our today's lesson is countable and uncountable sets. In math, we often have sets of objects, and these objects can be numbers, functions, or just about anything. And the object is called the element of the set. The number of elements in the set can be either finite or infinite. For example, you might have 10 elements or 1000 elements in a set. This is finite set. On the other hand, we might have an infinite number of elements in the set. So, firstly, we should understand the difference between finite and infinite sets. But let's look through what we will learn today. We will learn countable sets, uncountable sets. We will do some examples of this topic, and let's learn cardinality. So, firstly let's start. Think of a set of numbers. 1, 2, 3, 5, 7, 9. Okay, this is our set. This set is finite. This set is finite. As you can see, we can count the elements 1, 2, 3, 4, 5, and 6. It has 5 elements. It has 5 elements. And the cardinality of the set is 6. The cardinality of the set is 6. So let's recall what is cardinality. A finite set is always countable. Is always countable. And the cardinality is the number of elements in the set. Is the number of elements in the set. So here we have 1, 2, 3, 4, 5, and 6. We have 6 elements in the set, and the cardinality of our given set is 6. So let's learn what is infinite sets. What is infinite set? Consider a set of numbers, which contains all, I highlight all the integers greater than 10. All the integers greater than 10. For example, 11, 12, 13, 14, and etc. These dots means infinitely many elements. Infinitely many elements. So, we know that our given set greater than 10 is infinite, and we want to decide whether or not it's countable. As before, we mentioned that the set of elements from 1 to 5 or 1 to 10 is finite, and all the finite sets are countable. But what does it mean, the set countable? Let's learn. Definition. A set is said to be countable. A set is said to be countable if its elements can be placed in one-to-one correspondence, in one-to-one correspondence with the natural numbers, with the natural numbers. In this case, we say that the set has the same cardinality. The set has the same cardinality as the natural numbers. But firstly, let's recall what is one-to-one correspondence. So, suppose we have two infinite sets. One is the set of odd numbers, and the second is the set of even numbers. If we can match each element of this first set with each element of the second set, we say that these two sets have one-to-one correspondence. For example, we can match 1 into 3 in 4, 5 in 6, 7 in 8, and etc. As you can see, no element is missed. So there is one-to-one correspondence between these two sets. Finally, let's summarize. Each element of the first set is linked. Each element of the first set is linked to one-to-one correspondence, linked to one and only one element of the second set. Linked to one and only one element of the second set. So let's see another example. For example, we have the set of elements of circle and set of elements of rectangle. Suppose that the correspondence between them is like that. Okay, this is not one-to-one correspondence, because look at this set, the second set. Here, yes, the first element of the first set is linked to first element of the second set. But look at the fourth element of the second set. This square, this rectangle, is linked with two elements of the first set. But in the definition of one-to-one correspondence, is said that its elements can be placed in one-to-one correspondence with the natural numbers, and one-to-one correspondence means that each of the first set is linked to one and only one element of the second set. But here the third element of the second set is linked with no element of the first set. So this is not one-to-one correspondence. To show that, as you remember, the set greater than 10 is countable, we need to show that its elements can be placed in one-to-one correspondence with natural numbers. In one-to-one correspondence with the natural numbers. And let n be an element of the set n. Be an element of the set n. This is natural number set. As you know, it starts with 1 and it's infinite. Define a function fn is equal to n plus 10. So then fn is an element of the set greater than 10. So let's summarize. For example, assume that we have natural number set and there is a function defined on this set. The function is fn is equal n plus 10. Then fn is the element of the set of the numbers greater than 10. Plug 1 to here. 1 plus 10 is 11. 2 plus 10 is 12. 3 plus 10 is 13, and etc. Now we say that fn is equal to n plus 1 is a bijective function between the two sets. So it's obvious that if we have a bijective function between our natural number set and our given set, so then we can say that these two sets are countable. Okay, our first set is 1, 2, 3, 4, and etc. Our second set is 11, 12, 13, 14, and so on. As I mentioned above, if I plug 1 into here, our result will be 11. If we plug 2 here, our result will be 12. If we plug 3 here, our result will be 3. And as you can see, no element is missed. All the element of our first set can be matched with all the element of our second set. So let's summarize what we have said. If there exists a bijective function between two sets, this means they can be placed in one-to-one correspondence. So any set which can be connected to the set of natural numbers, any set which can be connected with the set of natural numbers using a bijective function like that must be countable. So informally, to show that a set is countable, we have to show that no elements will ever be repeated, and no elements will ever be missed out. No elements will ever be missed out. If these two conditions are satisfied, we can say that our set is countable. So let's answer some questions. For example, suppose the set of integers, we claim that the set of integers is countable, and let's show why. We can count the elements like that. We can count the elements like that. This is the set of natural numbers, and this is the set of integers. The set of real numbers start with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and etc. So we can start with 0 and continue with 1 minus 1, 2 minus 2, 3 minus 3, 4 minus 4, and so on. And we can keeping going like this. As you see, we will never miss out any of the integers. And never repeat any of them either. So the set of integers is countable. So let's continue. This is our second example. The set of rational numbers Q, A over B, such that A and B are integers and B is non-zero, is countable. And let's show why. We can count the elements like this. So here is our set of natural numbers, and here is our set of rational numbers. Let's start. As you know, the natural numbers start with 1, continue with 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and so on. Let's start the set of rational numbers with 0 again and write the fraction as the denominator should be 1, and we should write the numerator minus 1 also. And let's continue 2 over 1, and let's continue this order with 1 over 2, which the denominator should be 2, and also minus 1 over 2, but we can't repeat 2 over 2 and minus 2 over 2 because 2 over 2 is equal to 1 as we have written it, and minus 2 over 2 is written here. The results are the same. We shouldn't repeat the same numbers. And let's continue. Minus 2 over 1, 3 over 1, 3 over 2, 2 over 3, and keep going. 1 over 3, minus 1 over 3, minus 2 over 3, minus 3 over 2, minus 2 over 1, 4 over 1. As you see, we didn't repeat 3 over 3 and minus 3 over 3 because the results are mentioned before, and 4 over 3, 3 over 4, and keep going. This method will provide a one-to-one correspondence between natural numbers and rational numbers, and we said that if we can provide one-to-one correspondence, then Q is a countable set. So let's summarize our today's lesson. We have learned that natural numbers, integers, and rational numbers are countable. And what is countable set? Countable set is a set that we can provide one-to-one correspondence between the set of natural numbers. But the set of rational numbers and the set of complex numbers are uncountable. Why? Because the elements of real numbers, I mentioned a rational number here. This is not rational number, this is real number, this is rational number. Okay, the elements of real numbers cannot be placed in one-to-one correspondence with the elements of real natural numbers because some digits will be repeated and some digit will be missed out, and so the set of real numbers and complex numbers are not countable. So finite set, remember that finite sets are always, I highlight always countable. Infinite sets may be either countable or uncountable. And finally, if an infinite set is countable, infinite set is countable, it has the same cardinality. It has the same cardinality as the natural numbers. So this is our today's lesson, and see you in our next lesson.